Fantastic. So it's my pleasure to introduce Stephan Weiss. So he's roboticist, born and bred. So he has that sort of foundation and was doing some absolutely fabulous work on filtering. So he's done a whole stack of work before he even got into Equivariant, so understanding state estimation in robotics and observability and stuff like that. And then he started to get into Equivariant about 4 or 5 years ago, and has really brought that perspective, observability, and some of those understandings into the subject. So it's been a pleasure working with him, and so I didn't do any preparation. So I know that you're a professor at the University of Edinburgh, and that's all I'll say for the moment.
All right, thanks very much. I hope the microphone is working well. Yeah, thanks for the kind introduction. I definitely second the pleasure of working together. Come back to that in a minute. But first of all, thank you all for being here. I see now a full room, so 8 o'clock was too early. And thanks, Jake, for taking that bite. I hope we got the brains activated. We go a little bit less deep into math, so I reckon that we really go into the details of the formulas. As Rob mentioned correctly, I am a roboticist, still am. I started to go a little bit more in math 5 years ago when I started to work with Rob. It was a privilege to actually build up that connection. Since then, we have a very close collaboration on this equivariant state estimation aspects. So that actually quite changed a couple of things, how to look at these elements. And I'm well aware where probably many of you are, that basically are in the robotics topic. And now all of a sudden you should actually do math in robotics. And that's, that's a little bit, discomforting sometimes. But I can assure you it's paying off, right? And that, so we had a nice dinner yesterday. We actually all agree that roboticists should do a little bit more math these days and go a little bit more into details. So, yeah, with that, you see it already in the slide. So there's not only Rob as a person, but also people in his group. So Sean and Peter in particular, were mostly focusing on that work. When Rob said I was doing the work in state estimation, it was actually Alessandro, Martin, and Giulio in my group. I was merely the supervisor and doing the talking today. Good. With that, we dive into some specific systems today. So not any arbitrary system, but the ones that are hopefully most interesting for robotics. For mobile systems, it is the aided inertial navigation topic. So with that, we're basically looking at the IMU at the core. So as a navigation sensor, we integrate that sensor and then have potentially some correction sensors, GPS, camera, magnetometer, pressure, whatever. But the core item is essentially the IMU. And when we started working, when I looked a little bit more into the state estimation topics, I realized that the geometry of that sensor, the IMU, is actually still not very well understood. And that's when we opened the channels to Rob's group, when we dove a little bit more into the mathematics and how to actually capture this structure that is underlying in the IMU, all with the goal to have better state estimation. Better means more robust, resilient, have better convergence, faster convergence. And in particular also what we looked for is the consistency. By consistency, I mean that we have a certain estimation of the uncertainty, and that uncertainty should hopefully include the actual real state, right? So that the estimated uncertainty is correct in that sense. So these are the 3 topics. I will come back to that at the very end, where actually equivariance can help, and we see some tremendous improvement in this area. And that was the main motivation to actually go in this direction, because the equivariant theory was able to capture really the geometry, the structure that was underlying the IMU, in particular the biases of the IMU. And so there has been work in the past, including IMU structure, but not with the biases, and that was really a little bit the game changer that we added here. Good. For the menu, I will actually take you back a little bit in history. So despite the great introduction of Jake, I will bring you a little bit into the introduction of filtering. So we start actually with the common filter, right? And before you leave the room, because you know everything about that, it's a means to basically introduce a little bit of terminology and then thinking processes that we will be leveraging in the extended common filter. Bring that then to the thinking concept of groups, how to use Lie groups and geometry in the estimation process. We go through the I would say still today state-of-the-art invariant extended common filter, and then port that further to this equivariant concept. And that's actually where we then hit the core of the of the explanations here of the lecture, not to say talk, where we talk a little bit about nice groups. So what are nice symmetries that we're looking for? What is this global error, as Jake mentioned? So that's actually when we touch the topic again. And then we also look at how can we include the measurement. So not only look at the dynamics of the IMU, but then how can we actually correct these dynamics with a certain output, equivariant output in the ideal case. At the end of the, so after that here, so we basically have all the theory, all the knowledge and the insights on the equivariant theory. And from there on, it's probably a little bit more of a PR talk. So what we achieved so far, where we really see the differences in practice, and then go for some insights on implementations, right? So that's a bit more the lighter stuff then. Good, but let's start with some math again, but very easy math in this beginning. So just also to bring across a little bit the variables. So in a regular Kalman filter setup, we have well, xi here, xi dot the dynamics as a linear system with some dynamic matrix times the state xi, and then some manipulation of the input u. Then once you have this linear equation, linear dynamics, you can then essentially propagate also the uncertainties in that system, all assuming that you have some Gaussian distributed random variables. So you transport that from the previous state to the next state. You also include the uncertainties of your input, and that's in the regular covariance propagation in a Kalman filter. You can also design some output with a measurement function C, so the output Y, estimated what output Y hat, and then the state xi hat. So there's a little bit of terminology symbols that we're using here, and that from the equation point of view, I hope is very familiar and totally clear. Now we can do something that is actually quite meaningless for linear systems, but let's do it for the sake of education here. We don't do the estimation on the regular state, but you just build the error, right? So you can do that. It's meaningless because it's all linear, so we'll basically end up in the same thing. But we can actually build the error, error being defined as the actual state minus the estimated state. And if you go into further that, well, we have an error, something there in this state representation, and you can actually apply a chart for local coordinates if you want. So we will not talk too much about that yet, but just a little bit of intuition there. So let's stick with the error for the moment. We can then take the derivative of that error, arrive at a very simple equation. Here we have dynamics of the error. And then mind you, this is already something interesting because the input doesn't really appear because it cancels out, right? So we have essentially BU minus BU when you can compute the error. But what remains is actually the noise of the input, right? So the variation. So that's already something a little bit different. Nevertheless, of course, the propagation of the covariance matrix really stays the same because we're still in the linear system, right? So there's no magic in there. Mind you here the indices, so this is the covariance of the error. So if we go through that formulation, we're estimating the uncertainty of the error, but we are propagating the state, right? So there's a little bit of a different element there. We can also formulate the error in the measurement, have some error, some weighting of the error state here. And then once we have that, we can apply the regular Kalman filter update for our state correction and the covariance correction. Also here, the covariance correction is in the error formulation. The update here is on the error, and then we just add that to the other state to basically get the corrected state. Yeah? So far, so good. That was in the 1960s, so that's things evolved, and then we went actually to nonlinear systems. And let's see how their things changed and basically was applied to nonlinear elements there. So we have here the dynamics of the state is now a nonlinear function, f of xi and u, so the estimated state and the input. We do still have the propagation of the covariance for our state and the nonlinear measurement for our output, right? Now here, let's assume that we're still in Euclidean space, so no rotational elements, no multiplicative states, so all additive states that we can do. Then we can just say, well, our error again is the difference of the true state and the estimated state. We can apply some chart if you want. Then we take the time derivative of that error formulation, so that will be some nonlinear function, but here including the estimated states, right? So we can have a function of our error state, but also we will still have our states, our estimated states in the function. Now, when we take the Jacobians of that, then we see the first issue actually, that these Jacobians, they do depend on the estimated states, right? So whenever the state is wrong, we do essentially have a wrong linearization point. And that's really the key problem for these type of filters of the extended common filter, that, for example, initialization procedures, when you really have no idea about your state, you have a very, very wrong initialization point, and that can actually cause the filter diverge or actually to break. So people realized that, of course, and then they started to mitigate things with the uncentered common filter, have a little bit better uncertainty representation, iterative extended common filter to overcome all these linearization problems. But that was actually not really the core problem, right? So the core problem is really the state dependency that we have here, and we need to get rid of that, right? So having that at this point, so we're still in our end, and we can just basically apply this, the Jacobian of that, propagate the covariance, formulate our update equations as for the regular common filter, and then we essentially are done with that. When we move now to nonlinear common filter, so the extended common filter with multiplicative states, then things change a little bit, right? And then the community started to introduce this so-called box operator, which is box minus, box plus, but we can still then formulate the error in this fashion. So we have the error formulation with some true state, and then the box operator minus the estimated state, right? And at this point, it really starts to make sense to think about this error term and if we can actually represent that in better coordinates, right? As a very practical example, and this is basically what also termed this variant essentially of the extended common filter, the multiplicative extended common filter, or some people name it the quaternion extended common filter. This is very specifically designed for dealing with this attitude, this multiplicative state of the attitude, right? And then we had for taking the quaternion Q, the true quaternion defined as the error quaternion, delta Q quaternion multiplied with a estimated quaternion. So that's for the multiplicative part, and then for the additive part, or for the biases, for example, of the I mu, it's still regular additive elements that we can apply here. Now, here for the chart, using the delta Q, this is still a 4-element, right? Whereas the attitude essentially has a representation of 3 dimensions. Then we can use the chart or representing the delta Q as our small angle approximation with the real part as 1, and then we have some direction in the imaginary part of the quaternion, right? And then we can actually just build the estimator around A here, right? So around the direction. And this is a 3 vector, so minimal representation. And this is exactly what we talk about the chart, basically have a representation of these local coordinates, right? Now, taking all the insights that we had before with the common filter, extended common filter in the Euclidean space, we can go ahead, design the dynamics with our nonlinear function, right, for the state. So with that, we propagate the state. But then to actually estimate the propagation of the covariance, we do look at this error formulation, right? So we need to have a look at the error formulation, then take the derivative, right, of this error formulation in these local coordinates, and then we arrive at these dynamics of the error in the local coordinates, epsilon dot, right? If we do that, so omitting all the derivations here in this talk, there are numerous papers that talk about that. In particular, Nick Trani back in 2005 had a nice tutorial paper on that. Then you arrive essentially at these equations, these dynamics, right? So A for the multiplicative state, and then the delta B as the error in the biases. Now, when you look at this dynamics here, then you realize that they're actually they're linear in the error states. So A hat and delta B. So when you take the Jacobians, the only thing that is in the Jacobian is the input of the angular velocities and constants, right? So it's not dependent anymore of the state, and that actually leads to much better performance of the state estimation. We're still estimating the covariance in the error space, right? And then propagating the actual state, right? So with that in mind, we can then also design the measurement or the output of the system. So with some function of the error measurement. Error measurement then is essentially the value that we measured as attitude, and then the estimated measurement gives us a delta residual, so to speak. We can map that also to the local coordinate, and then we have the residual in the local coordinates AI. So here we assume that we just directly measure the attitude for simplicity, right? So there's no lever arm or other rotations in there. So once we have that, so we have the residual in our local coordinates, right? So the AI in the error formulation. Then we can formulate the Kalman gain, the update, etc. And then here is something that we will see afterwards in the equivariant formulation again. So here the gain or the residual times the Kalman gain, this is still in the local coordinates, right? So we need to map that back to our error state, and then only then basically multiply that or add that to the actual state. Please, question. Theta, this one. So this is just a map from our error definition here, or as an example, the delta quaternion that maps it to a local coordinate, or in our case is A here, right? So the direction in the three imaginary parts of the quaternion.
Generally speaking, the local coordinate is what for
Say again?
Generally speaking, for other states, what is the local coordinate?
That really depends on the chart. So we will see afterwards when we have Lie groups. You can basically take the logarithm of the Lie group, and then you have essentially go to the Lie algebra, and then you take the V operator to go to a 6-vector or 9-vector or 3-vector, depending on the structure of your Lie group. Yeah. So we'll definitely talk about that theta again, but this is as an example here in the quaternion case. Yeah. Mm-hmm. Good. So this is an important element here. So we have the update in these local coordinates. We need to map that back into our error formulation, delta Q, and then only we can update our state in this update process. For the additive states, I mean, it's trivial. We just have the Kalman gain and then add that to the previous state, right? So there's no mapping required there. Good. But this is actually really the first time that people started to look at geometry, to look at a little bit more at the structure, what is actually underlying there. And it really marks a little bit of a tipping point in the thinking process.
Yeah, so just to be fair with the history, this was done by Markley and Schuster in like the 80s.
Yeah.
Yeah, so, yeah.
Yeah, okay. I mean, do you mean because of the Chani paper? Or
I just mean like a multiplicative returning like the Kalman filter was really pioneered by not Schuster.
Yeah. We had a nice comment from his co-author actually on the JPL notation and the Hamilton notation.
Yeah, that's a whole.
Yeah. we have a nice paper on that actually. So this is yeah, definitely. So thanks for that. So this is
yeah, they did.
Yeah.
And they even did the reprojection. Wow.
Did the reprojection? They even had the curvature terms.
Yeah.
If you threw the curvature term out, make no difference. They got that wrong. Yeah, still good. He didn't have the curvature concept. He took second derivative.
There's like a reset step still.
Yeah.
For the covariance.
Yeah.
Anyway, I'm just trying to say. Yeah. To be fair.
Yeah, absolutely. Yeah. It was not the invariant before the MEKF, right? It says that,
a multiplicative form.
Yes. Absolutely. Yeah. And it has been before the 2005 paper here, of course. Yeah. This is absolutely. Yeah, thanks for that. It is also JPL, by the way. Tron is, I guess, is still there, if I'm not mistaken. Yeah. Anyway, good. So that's, I guess, on the years. So thanks for that. On the sequence, we still basically have this linear aspect on the Kalman filter, and we have this nonlinear effects here as the extended Kalman filter. With all the different mitigation strategies with the iterative Kalman filter, unsended Kalman filter, and then also some particle filters, which is a slightly different flavor. And then here with the multiplicative Kalman filter that starts to consider a little bit geometry and the structure underneath that. And then that triggered some thinking processes, and this invariant Kalman filter concept came up and really embedded most of the elements into this Lie structure and have up to like really exact linearization concepts under certain conditions, right? And based on that motivation, essentially, we went further, and this equivariant concept was a little bit more of an envelope then covering the equivariant filters and the invariant Kalman filters as a complete design theory, as we would like to communicate here in this in this workshop as well. Estimation on Lie groups, so very a little bit of a figure. What we're talking about here is when you're on a certain manifold, on a certain structure, you just apply linear linear propagation. Then you can easily wander off this structure, and that is really the core element that then is impeding you to have consistency, large beacon of convergence, fast convergence. It just basically breaks the whole structure. Right? And then the multiplicative extended Kalman filter did a better job, but is still breaking to some extent with the certain assumptions, and then have not quite the true linearization there. Now, with the invariant Kalman filter, under certain concepts, or you have a Lie group where you have an affine system, then the authors actually prove that you have an exact linearization, right? And this is a very strong statement. So you're exactly on the group, your covariance is exactly represented on that space. And that's really as good as it gets, right? So you essentially then have a linear Kalman filter in that space. Given certain structures, right? So given the Lie group, given the affine system. And what that actually brings to play in practice, and this is really interesting for photosynthesis, is that the covariance in particular and the whole representation of the state is just correctly represented, right? So if you have on the left side in green, the true evolution of a robot state, so there's a Monte Carlo sampling, and this, by the way, from the paper here of Ross Hartley, then we basically get this banana-shaped distribution, right? Depending on the uncertainty of the yaw and also the uncertainty of the translation. Now, if you use this quaternion-based extended Kalman filter, we still get a decent shape, but it's just not exactly representing the true distribution, right? Whereas if we're really leveraging the structure that is underlying the system with this invariant Kalman filter, in this case, the right invariant extended Kalman filter, then we really can show these distributions correctly in space, right? It actually goes as far as when you start on a specific point and you have no idea about your yaw, then intuitively, well, you can be anywhere on the circle of that initial point, right? And that's exactly what the authors show here in this picture. So you start in the middle and then you go off in a completely uncertain direction, and then the invariant Kalman filter really captures that uncertainty very, very properly by leveraging the full structure of the system. Good. So let's have a look how this works a little bit more in formulas, because we will then use that example specifically to bring forward the concept of the equivariance. So for the invariant Kalman filter, we have as a state, we have rotation, velocity, and position, nothing else. So at the moment, no biases of the IMU, which is an element of the SC23. In the paper, they show that we have essentially this dynamics here of our group, capital T, which is this element of SC23. And that's essentially then our propagation of the state, right? Now, using the concepts that we talked about in the past, with the Kalman filter, extended Kalman filter, multiplicative Kalman filter, we can also design here an error state with this box operator, which is essentially then the true state minus, or in this case, the group inverse of the estimated state. And since we're in a Lie group, now it really makes sense to have this chart, and this is basically the question that we had before. So here, the theta is essentially this logarithm of the Lie group, right? And then we're basically in in the Lie algebra, we take the V operator to put that Lie algebra matrix into a vector, in this case, a 9 vector with 3 on rotation, 3 on velocity, and 3 on position. So that gives us essentially a 9 vector and the formula for this error here, and we can take the temporal derivative of that formula to arrive at our error dynamics, right? Why do we need this error dynamics? Because we basically can then linearize that for our the dynamics matrix for the error, some modification of the noise of the input, and then we can use that to propagate our covariance matrix. Right? So again, here, same concept. We have the state dynamics, and we have the covariance here in the epsilon space, in the error state. And if you look at this dynamic matrix very closely, then we see something very interesting that I mentioned before. We have a constant here. So this is gravity, and this is identity matrix. So it's a constant matrix. Now, if you look at this equation, it's a Kalman filter, right? Essentially. And that's really strong because that, and then in the paper, actually, the authors show that for this specific case, this is an exact linearization, right? So it's not even an approximation. So that's the main finding of that paper, and that is what makes essentially this invariant Kalman filter so strong and so exceptional. Good. With that, now people really realized, and hope this is historically correct, that looking at the structure, looking at the geometry is really worthwhile doing so, right? And there was this thing that it's only valid for a fine system on Lie groups, and when you add the IMU biases in particular, and this is really the problem for roboticists, right? Because everybody works with IMUs, and everybody has this, noisy IMUs, these MEMS type IMUs with the biases. So not adding biases is really a nuisance, right? And then, of course, the authors had provided some remedy for that, some mitigations to tack on the IMUs as just a 6 vector for rotational biases and acceleration biases, but it really destroys this nice mathematical background that we have, right? So basically, you have this beautiful mathematical concept, and then you just tack on things, right? And that was basically the motivation to look further how we can incorporate that information a little bit more neat, more cleaner into the whole concept. And this is where this equivariance comes in, and this is where we do a little bit of a switching in the concept, right, in the thinking process, because so far we just talked about the state, right, and the error, but it's always the state, the manifold. Now, let's take that thinking process a little bit further and say, well, yes, our physical state lives on that manifold, is a position, is an attitude, but actually, and that's also what Jake also mentioned in his primer talk, we can also, modify that state with some action, something, abstract, with a symmetry, with a group action, and then port that, model that to our likings, hopefully that we arrive on a Lie group, right? And then we can do the whole estimation there, right? But that's a little bit more abstract, right? So we're not talking about position, attitude, etc. We're just talking about the rotation, 3 vector, and whatnot, right? So we take that to the new representation, do the estimation there, and then we just need to make sure that we have some connections between the two worlds, right? And there's some connections is something that we need to talk about. In particular, here this phi action then takes, for example, a element of the manifold with an action again to the manifold, right? So with essentially this transitive property that Jake already mentioned in the primer talk. So let's take that thinking process to the example of the invariant Kalman filter. Then we still have our state, the physical aspects, right? And we usually call that the torsor. So it's essentially the physical elements that we can grasp and think about. And then we have this abstract group, X here, which is A, B, and D, A being the rotation matrix, B and D being 3 vectors, right? So before, we still use that X kind of implicitly, but as another T, right? Now here we're talking about abstract elements. And also that X here has some dynamics, right? And following the primer of Jake, we know that, this temporal derivative is X times something in the tangent space, right? Basically velocity. And then this is really the connection also between the two worlds. It's, this capital lambda is what we call this the lift, and this defines really the dynamics of this abstract element here in the new group, right? So this is basically the motion. When you have the motion f of psi and u in the manifold, we have the lift essentially that drives here the group element on the symmetry. Now, how to find this lift is essentially the question, right? So we basically need to define a map here, an action, phi action, where we have x acting on a manifold, putting that psi 0, so any point on the manifold to another point on the manifold psi by having this group action phi of x and psi. Now, for the invariant DKF, we just define this action as a t and x. Basically, have a right multiplication, and that really essentially looks very much like the error that we had before, right? So we just had t and t inverse before. So we have t and x here, and then we can define that error and or the state with this connection with the phi action, take the temporal derivative of that, and then we should actually get, you know, what we look for in x dot. So when you do that, we have the temporal derivative of our state, psi dot or t dot, capital T dot, is our input function here, f of psi and u. And then we just take the temporal derivative of the right side here, which is the differentiative derivative that already Jake mentioned, in the direction of our lift, of our lambda, right? And then that results in being capital T times the lambda, which is our velocity basically that we apply, and then we can solve that for the capital lambda element here, right? So psi dot is our function over here. Then we can basically have the connection between these two equations and then solve for capital lambda, right? Good. And then this is our lift, and this defines the motion on our symmetry, right? And one second, and we can do that. So this so far we didn't talk about equivariance yet, right? So no properties. So we can just have a transitive group action on the manifold that brings us from one point to the other point. Once we have that, we can define the lift and then basically work on the manifold, on the symmetry here. And we can do that with anything. So no equivariance requirement there. Yes.
At high level, in this example, we're already in the manifold, so we already have a nice structure. Like we already our state is in the manifold. So what is the key thing that we want from our lift? Like what do we want the dynamics of in the lifted space to settle? Like what is
Yes. So you're asking about the goals that we want to achieve, right? So far, with this concept, we didn't imply any restrictions, right? So really, the only restriction that we need to have is it's a transitive group on a manifold. That's all, right? But then we're basically, and this is really a good question. So now we can do that. And what symmetry, what action should we actually look for, right? So what are the good symmetries? And I think the next slide actually answers then your question. So one thing is that a symmetry that satisfies equivariance, for example, that would be the best thing, right?
Maybe just add, I think maybe part of it is that this example SE3 target group.
Yeah.
You might want to three where the state is not.
Yeah. So that.
Yeah. True. Mm-hmm.
We want dynamics that have certain.
What I'd say, having worked in the field, is the original problems were only groups, and people did some stuff, and they found these errors, and they started doing derivatives, and it all worked. And it was really hard to know what was going on. And so what Stephan's doing here is he's saying, no, you should think of it as a manifold and a Lie, and then think of the errors constructed between these things in the way he's describing it. And then you can understand the general theory. And then it also generalizes, right? But you can do it all just by in fact, invariant extended Kalman filtering doesn't introduce this. It just says, you know, use this error and look, magic, right?
Yeah. Thanks. Yeah. Mm-hmm. Yes, yeah, exactly, yeah. So this is very, very roughly speaking, it's really the temporal derivative of that equation here, right? Yeah, so this is in the Lie algebra. So this is the velocity, right? So you have essentially your manifold, and then you have a certain point in which direction you want to take the Frege derivative, right?
There's an X right? There's
You mean in this line?
Yeah.
No, but this line matches to this part here, right? So here on the left you have only Xi, so basically the state, and then you have the action, the phi action, which is dependent on the of the symmetry that you already the group that you basically detect on the manifold and Xi. Yeah. So yeah, so this is the variable, right? So you're solving for. So this is the velocity direction that you're taking the derivative from. Yeah. But it's a good question, right? So this is really essentially the slide how to read these equivariant papers, right? And it really shows you a little bit where things come from. But it's essentially really this temporal derivative where you want to have this dynamics done, and then you have an expression for lambda, and then you can solve for lambda, right? Yeah. Yeah. Yeah, exactly. Yeah, because that's really the linkage between your state, the torsor, and the group, right? And you want to preserve that link, and you want to have essentially then, that is then the lift essentially. Right? Hmm? Yep. Good.
One more perspective.
Yeah, sure.
You go back one to the slide. So yeah, like what's on the right here with Xi is this could be on like a familiar Lie group, but it could also not be on a familiar Lie group. But if you look at the left, x dot equals x lambda, that looks exactly like r dot equals r omega cross, like identical. And then there's all this theory on how to design observers for systems that look exactly like that. And then you can just kind of turn the crank in some sense on, once we have it in that form, you're going to turn the crank on all these nice observer design tools. So one of the ways I like to think of this is we want to get this into a, like what Rob said was absolutely correct, but another way of thinking of this is we want to get to a form that basically looks like Poisson's equation, because we know how to work with Poisson's equation.
Yeah, thanks for this perspective. So this is really what the workshop is about, right? So get different phrasing, different wording, different viewpoints. Another one, yeah.
Very simple question. What's the importance of distinguishing between defining a torsor and calling it a group?
It helps you in the thinking process, right? So it's really with the torsor, it's really this physics, the graspable things, and then the rest is what's abstract, right? And it helps you. I mean, when you talk to peers, it helps you a little bit better distinguishing what you're actually meaning about. But maybe Rob, you have.
Could I answer a question? So when you take a robot, right? So take a robot pose, right? So I've got an attitude and I've got a position, right? That is not SE2, right? SE3. That is not an element of a rigid body transformation. It's a set of coordinates place. And that's the thing that we're really trying to get at. That when you actually write down the state of a robot, it's not an element of a group. It's a set of coordinates of meaning something, right? And then you introduce the group on top of that. So that's why we use the term torsor.
I thought of both would be the same so far. I do think of it as coding. So
Yeah.
I think of it as
Yeah, so I mean, go back to the books of Spong and Vityasagar and everything. You know, I remember Spong's book. It's got a page that says, you know, here's homogeneous coordinates, and it means coordinates, and it means rigid body transformation, and it means a coordinate transformation. And they say there's these three things, and they're all confounded, right? And it's taken me 20 years to unconfound them in my own mind, right? Because when you actually do observers, you actually have coordinates, the things that you actually care about. And then on top of that, you start talking about, you know, what's the group action that you want, right? And for pose, you know, there's 2 or 3 that you could choose. You could choose a direct product, or you could choose SE3, or there's, you know, a bipolar one that we're starting to use for radar and stuff now. So what's the symmetry? But the coordinates don't change. Okay? And the symmetries do change. And so that's the important part to get in your mind.
So when we pick the state, you don't need a group.
Group,
Then
exactly.
the last one, because
That's it.
that's the leftover of the invariant theory that I have to think of the state and a group at the same time.
Exactly.
But
Yes. And it's hard. I think one of the things about this subject is it's challenging because we've all done a robotics course, and that idea that the homogeneous coordinates is the pose is an element of SE3 is really deeply embedded, and so you've actually got to break that to then be able to do this. Yeah, so it's challenging, right? It's one of the barriers. I'm talking to. Sorry.
But it's I think these are really great insights, yeah, and much more clearly phrased than I have. But this really is this these physical elements versus this abstract parts. Yeah. Good. Well, thanks for that. Let's try to keep roughly in time. Back to the question: what properties that we're looking for? One is the equivariance. Jake already mentioned it a little bit with this graph. So this is another way to show these graphs that we have seen in the primer. A little bit more in detail. So equivariance, when we start from a certain point on our manifold, and we basically transform that to another point with our group action phi, and then applied the transformed velocities here, or basically the input, then that should be the same as if we apply first our dynamics and then transform that onto that point again, right? So this is really the 4 elements that we already saw in the primer. I think I can keep that fairly quick, but this is one property that we're looking for. It's not mandatory, right? So far also for the lift, we didn't imply equivariance as a necessity, right? So it's a nice to have, but it's really nice to have, right? In particular for the state equivariance here for the system dynamics, which comes along with the input equivariance. If you talk about the measurement, we also found that we can just basically tack on the measurements without equivariance. Now, what is more beneficial to aim for system equivariance or output equivariance? We have not a clear mind yet. There might be opinion in one or the other direction, but this is certainly one thing that you could aim for, to have this equivariance in your state action phi. So this is one way to come up with a symmetry, then check for equivariance. If that's equivariant, then you're happy and you go forward. So with that, we can then formulate actually the equivariant error, as we have also heard in the primer. And with this mapping, with the phi action, so we map a certain point psi 0 to another point on the manifold. Then we can also say, well, if we have a certain point on a manifold and we have the exact correspondence in our symmetry, we can map that back to psi 0, right? Now, if we don't have the exact element here, but we have the estimated element psi hat, then we will not arrive exactly at psi 0 anymore, right? And this is exactly the error that we're talking about. So we can define this equivariant error, which is essentially this global error that maps this original psi 0 through the true state and the estimated state, essentially through our error here in the group to the error on the manifold here, right? And this is really very similar to what we have seen before with the common filter extent, common filter, and so on and so forth, right? Just now with this global error definition, but we still have an expression of our error on the manifold. We can then still apply this chart to our epsilon. We can still define then the temporal derivative of that equation, and then we have our error state dynamics as before, right? So that concept really stays the same. It's just now with a different initial aspect here with the group element. So without going through much through the whole details and derivations of these dynamic matrix, so this is just quite a mouthful to take the temporal derivatives. But at the end of the day, you can approximate that as a dynamic matrix of your error and some certain distortion of your input noise. Once you have that, well, then you can apply the regular Kalman filter propagation equations. So we do correct the state, right? So we have here the old state, and then thanks to the Lie group property, we can then take the exponential of our velocity, so the lift here, and the covariance propagation really remains the same as before, right? Good. So that's basically on the propagation part. Now we need still to talk about the output, so output equivariance. So also for the output, well, generally we have a certain measurement function, h, that measures some, well, is dependent on one point of the manifold and gives us a measurement y0. We can also map that measurement into some local coordinates with a delta function here. And then we have the delta function of our measurement function that gives us our measurement y, right, in these local coordinates. If we have output equivariance, so output equivariance is defined as very similar to the other definition. So if we apply our action to our state and then basically generate the measurement, this should be the very same thing as having our measurement of our regular state and then applying a so-called output action rho, right? So if that's the case, we talk about output equivariance. Again, it's not mandatory, but again, it's a nice to have because it captures the structure of the underlying system more properly. So if we have an equivariant residual or error, then we can formulate that as follows. So we have the residual as some measurement in the local coordinates, and we can apply all these transformations that we basically have from the output equivariance. Interesting thing here, so without going too much into details on the equations due to time, is that this is accurate up to the third order, right? And this is really nice in terms of linearization properties and really helps in performance of the filter. If your output is not equivariant, well, then you can still formulate the error, right? So you just take basically the measurement of the true state minus the measurement of the estimated state, formulate that in local coordinates, you can linearize that, and you still have your measurement matrix, right? Dependent on your error epsilon.
So is delta also an action?
No, this is a chart essentially.
Oh, yeah.
Yeah. So it maps for your output y to some coordinates of your choice. Good. So also here, equivariance is not necessary, but it's desirable. But we can still apply the process of this equivariant filter design, right? And once we have that, so once we have this measurement matrix C, then we can start applying the regular Kalman filter update. So we can calculate our Kalman gain with our innovation matrix, previous state covariance matrix, measurement matrix. So this is essentially very familiar equations here. We can then compute the correction term, and this is slightly different, right? So just a little bit on a conceptual side. So here is the correction term in local coordinates, right? And we remember ourselves back to this slide when we had this exact notion on the quaternion filter, right? So we had this correction in these local coordinates. And then what essentially is the rest of the part is that we map that back, from the local coordinates and then back basically onto the group, such that we can then apply our correction as an exponential multiplied with the previous state, right?
Yeah, I have another question. So this came up, I was reading something the other day. So you have to compute that derivative with respect to the error.
This one?
No, the first d, delta equals d.
Yeah.
But you don't know the error. Like that little subscript e there, isn't that x hat?
Yeah, you don't know the error, but you have the expressions, right?
You evaluate it at so it's the differential function evaluates at the
Right.
Yeah.
Know that.
Yep.
Good.
Theta is its chart.
Yeah, I don't know if there's non-invertible charts, then you probably not too wise to choose. Yeah, no. Good. All right. Okay. So that's then the update essentially on the mean and the covariance as with the regular state estimation or Kalman filters. We talked a little bit about this correction term. I will not go too much into detail that, or actually not at all. But it's a certain element to consider, because when you have your error, you correct for that, and then for the next time, basically resetting things, right? And that needs to be considered on the curvature. But that's still active research. So happy to talk about that, and also with Rob and the other more senior persons in this equivariant field can definitely talk a little bit more in detail about that. Good. Then we have a big slide. I will actually pretty much skip through that, but this is really a summary that we have seen so far, right? So the main message of this slide is really we have a procedure for the, let's say, the equivariant estimator design, be that really with an equivariant symmetry or not, that is really not necessary, right? So we can actually formulate the whole process without having an equivariant system or output, but it's still the same process. We still think about a certain state, a torsor, then we have a certain group action, input action, and output action, if at all, right? And this is just a recipe we can go through. And then the question is essentially not anymore how we really define the error, but what symmetry are we choosing, right? And this is really a different way of thinking so far, because you have seen from the Kalman filter, extended Kalman filter, multiplicative, we always talked a little bit about different errors, but we always talked about states, right? And now with this concept, it's really, we're talking about symmetry. So what symmetries am I choosing, right? And then afterwards, the recipe is, you just go through it. And just to visualize that a little bit more properly, so when we go back to the beginning of the talk, the multiplicative extended Kalman filter, we actually used already this symmetry and this concept of torsor and the group. Now it's just that we had the rotation, and then the group element is a SO3 element, A, right? Just back then, we also used a rotation. Then velocity, right, is a 3 vector as a state, and when you use the group element A, which is also a 3 vector, just in the beginning of the talk, we also used the velocity, right? So this really, and I think goes a little bit into your comment, this different way of thinking of the torsor and the group elements, right? So, and these are all the previous estimators. They were all designed on the so-called natural symmetries, right? It's essentially the state and the symmetry. It's really the same, the same flavor, right? Same thing goes for the invariant extended Kalman filter, right? So we have this SC23 group. We have the state, right? T, and then just this SC23 group as a group element, right? Which have the same aspects. You can also pull that further to the two-frame invariant extended Kalman filter and so on and so forth, right? But essentially, it's really the state and the group is difficult to distinguish because they have the same aspects there. Now, when we go a little bit further, and this is really when we go to these equivariant Kalman filters that we've been working the past few years together, Rob and I. Then we see that state and group is not really the same anymore, because then we have the so-called tangent group, and this has a different element, right? So we have the state T, then we have a group action, just the same here for the SE23 element, but then for the biases, for example, to account for the biases, we're not just having here the tacked on elements as for the invariant extended Kalman filter, but we have the adjoint of the biases, right? And this action then actually allows to properly account for the IMU biases on the symmetry on the group, right? And this is really the first group that we found that accounts properly for these IMU biases and incorporates everything on this nice equivariant structure. We did need to include an additional state for that, so there was a little bit the downside. But with that element, we actually had a constant dynamic matrix in the core states, right? So we pushed all the nonlinearities to the biases. Yeah.
In this equation, the action of which symbols are the group elements?
Bold is non-bold are group elements, and bold are state elements. Yeah. Mm-hmm. Yeah.
You push all the bias states outside of the matrix, so where they go?
No, so the core state, the dynamics of the core states are constants, and the nonlinearities go into the dynamics of the biases. Yeah. Whether it's good or not, I mean, that's to be discussed from it's a mathematical point of view. In practice, we see tremendous amount of improvements. Yeah. Good. So then, and then of course, the question is that the only group? Is there a better group or not? And then Alessandro actually went ahead and found a couple of groups that can include these biases of the IMU in one way or the other, right? So then we have the so-called direct position group, and that the property there is that we have a certain coupling in position with the velocity. But otherwise, we don't need an additional bias state here as we used for the tangent group, right? And that has an interesting property because it's really bad when you have unknown large initial velocities, because you have this coupling with the velocity, right? So when you're essentially initializing mid-air and your velocity is unknown, well, you shouldn't use that group, right? Then you should probably use this semi-direct bias group, which has a coupling in the velocity with the position state, right? But no coupling with the velocity, right? So that's much more resilient towards initial velocity errors. However, if you're initializing on a certain position and your position is completely off, then you shouldn't use this symmetry, because this has a dependency on the initial position for the bias dynamic, for the velocity dynamics, right? And it's really, you can find several different symmetries, and then what is best for you is really dependent also on the case. Ideally, you find a symmetry where everything is constant, as the authors of the invariant common filter did for affine systems. We're not there yet, right? So I don't know if that exists, but it's still a question. What symmetry is still a question. What is better than the other, right? And we haven't found yet a mathematical concept to actually describe that, right? What we found, okay, so this really marks a little bit the fundamental element for the IMU. And then, of course, if you add measurements or outputs, then you add another sensor, right? And then with that sensor, you add another physical element. So, for example, the distance of the GPS sensor to the IMU. And it's a question: can you actually add these states as well in the estimate? And if so, what effect does that have on the symmetry, right? So, is that easily plug in and plug out? And the answer is actually to some certain states, yes. So Alessandro in his thesis actually went ahead and listed a couple of elements there, where you have rotational position calibration states, also measurements in the world frame, so direction measurement or a vector state in the world frame. And then we found that this can be actually plugged in fairly easy into the existing symmetry. So looking a little bit at the time, just this very brief here, this example. So we have the IMU states with the rotation, velocity, position, the biases. And if you want to add, for example, a magnetometer, you have then this direction element and the rotational calibration matrix, right? And then if you add these states, you just go to the symmetry table, so to speak, define the measurements, and then add these elements on the symmetry, and then off you go, right, with the group action. Good. Last thing. What was that? The right or the left question? Yeah. So we will only touch that a little bit. It's still ongoing work. So we heard in Jake's primer, and there's the left and the right group action, the left formulation of the filter and the right formulation. There's a long debate on what is better and what is worse. At the time being, we know that if you actually apply the correction step, it's the same. If you don't apply it, then for some ways it's still better, that we can't explain and didn't expect, and for other ways it's not. Anyway, so sometimes you can actually transform your measurement. So if you design the right external common filter or right equivariant common filter, and you have a left measurement as for example the global position, then you can actually transfer that measurement into some body views, and then use that as a modified measurement, right? And you can still use that as a so-called transformed right measurement. And that basically really completes the concept of the procedure, where you have to choose a symmetry up to your liking. You test it for equivariance. You do the measurement cost if you want to need to have the right left and right connection. Check for equivariance, add sensors as you like with the different calibration patterns, and then you should have improved linearization errors and improved performance. Let me take that 1 minute until 10 past to show just a little bit of performance elements. So I will probably switch to the most important ones that I feel are most noteworthy. So these two graphs essentially are showing a multi-copter standing on the ground and doing yaw estimation, right, with position measurements. Now, of course, this is an unobservable state, because if you don't move, if you don't have acceleration, this yaw is not observable. Now, in green, you see the yaw estimate on the right here of a regular extended Kalman filter. And due to the spurious information that gets injected to the noise in the position measurement, you see that the yaw going all over the place. Now, for the equivariant formulation, because of this decoupling and basically leveraging of the symmetry of the geometry, then we see that this has actually no really effect on that, right? So this is really one benefit that you get out of it, that you really have the information that goes into the system is leveraged much better with the equivariant formulation. Another thing is, well, we talked about consistency. So here, just very quickly, 10 to the power of 0 is 1. So this is the good value for the average estimation error squared. And we see that also during the transient phase, these Kalman equivariant filters, so these are basically pretty much all the colors up to here, they are consistent already in the transient phase, right? So even if we initialize with an error, we have a consistent estimate of our uncertainty. And here, if you look at the MEKF, so this was the for a long time the gold standard extended Kalman filter approach for attitude. This really goes off in the knees and shows that in particular in the transient phase you have these inconsistencies that you don't want. Right? Fast convergence, very last thing. So this is a comparison between the invariant extended Kalman filter and an equivariant formulation. And we have a helicopter that takes off and then moves, right? So during the takeoff phase, you have very little information that gets injected into the system. And you see that the blue one is the invariant extended Kalman filter, and it struggles actually to extract information during that low excitation phase, right? Whereas the equivariant filter just leverages that geometry much better, it extracts that information much better, and converges much more quickly in the states. Right? Good. I guess we switch, we skip a couple of elements there. So this is just the system in action. So we implemented these filters on the real vehicle. So there's not really a computational overhead, right? So it's once you compute the matrices, it's an extended Kalman filter that you do. Right? Hang on, that didn't work. Good. Hang on. There we go. There we go. Good. Yeah. So also, so this is for very agile motions, right? So with the FPV data set of University of Zurich, and really this resilience and robustness of the estimator is shown very clearly here, that it basically just works. Also, the tuning of these noise parameters is much less sensitive than with the regular Kalman filter. Right? Basically, the noise is really turned to be gains, right? And doesn't really have to reflect the actual covariance in the beginning because of this consistency of the estimator, right? So with very little tuning, we achieved actually this performance here, in particular on the FPV data set. It was actually there was a workshop at the RSS and performed as best monocular framework in the competition. Good. Very quickly, so we've seen that there is a symmetry that incorporates the IMU with the biases, so the overall geometry. We have seen a concept for filter design, for modern filter design. If it's equivariant or not, you choose basically the symmetry, and then you have your recipe to go through. We can attach additional states to the symmetry, so there's in some certain cases we have this modularity that we can leverage. We basically have this equivariance as indication for better performance, but it's not mandatory, right? And it's still to be understood what is actually making it better performing than other symmetries. What is a better symmetry? What is a worse symmetry? And in a nutshell, the benefits of equivariance is really we have larger beacons of convergence, we have a faster transience, and we have consistency. Right? So that's a very broad statement at the end of the talk, and sorry for the few minutes over time. Thanks very much.